In the spring of 2006, a group of F-15 pilots at Nellis Air Force Base in Nevada flew into an exercise against a small number of aircraft they had never faced before. The exercise was called Red Flag, and Red Flag is where American fighter pilots train against the hardest scenarios the Air Force can construct. The pilots knew they were going up against F-22 Raptors. They knew approximately where those Raptors were supposed to be. They had every advantage of preparation and familiarity with the airspace. The results were not close. The F-22s killed every opposing aircraft in the exercise before a single opposing pilot detected them on radar. In debriefs afterward, the F-15 pilots described engaging targets that appeared on their instruments only at the moment of simulated impact. The Raptors were never seen until the exercise was over. The ratio that emerged from Red Flag and the exercises that followed became one of the most cited numbers in modern military aviation. In training exercises, F-22 pilots routinely destroyed opposing fourth-generation fighters at ratios of greater than 30-1. One aircraft, on a single sortie, would account for multiple kills before the opposing force had any information about where the threat was coming from. This was not an accident. It was the product of a design philosophy that Lockheed Martin and the United States Air Force had been developing since 1981, one that took the lessons of every air war America had fought, identified the single factor that determined who won and who died, and then built an aircraft specifically optimized to own that factor completely. The factor was detection. In every air engagement since the introduction of radar-guided missiles, the pilot who was detected first died. The pilot who saw the enemy without being seen could choose when to engage, from what angle, at what range, and with how much warning to the target. The pilot who was detected first had none of those choices. He was already inside someone else's engagement envelope before he knew he was being hunted. The F-22 Raptor was built to ensure that American pilots would never again be the ones detected first. That is a simple statement. Achieving it required 25 years, $66 billion in development funding, the most sophisticated coding chemistry in aviation history, an engine that could sustain supersonic speeds without using its afterburners, a radar that changes frequencies 1,000 times per second to prevent enemy systems from locking onto its signal, and a sensor fusion architecture that presents the pilot with a single integrated picture of the battle space, assembled in real time from every sensor on the aircraft simultaneously. What Lockheed built was not merely a faster or more maneuverable version of what came before. It was a different kind of weapon, operating on a different set of principles, inside a different envelope of physics. Understanding the F-22 requires understanding why the aircraft it replaced, as accomplished as it was, had already reached the limit of what was possible in a world where detection had become the decisive variable. By 1981, the United States Air Force had been operating the F-15 Eagle for 6 years. The F-15 was, by any reasonable standard, the best air superiority fighter in the world. It was fast, maneuverable, and equipped with radar and missiles that gave American pilots a meaningful engagement advantage over anything the Soviet Union was flying. In aerial exercises and the limited combat experience available, it performed exactly as designed. The Air Force was already planning to replace it. The reason was not that the F-15 had failed. The reason was that the Soviet Union was not standing still. In 1981, American intelligence was watching the development of 2 new Soviet fighter aircraft, the MiG-29 and the Su-27. Both were designed specifically to counter the F-15. Both were genuinely dangerous. The MiG-29 was a close-range dogfighter with exceptional agility. The Su-27 was a long-range, high-speed air superiority platform that combined the range to reach deep into NATO airspace with the performance to threaten the F-15 on roughly equal terms. At the same time, Soviet surface-to-air missile technology was advancing rapidly. The S-300 system, which NATO designated the SA-10, was entering service with engagement envelopes and radar capabilities that could threaten aircraft at altitudes and ranges that had previously been considered safe. A conventional fighter flying into Soviet-defended airspace in a European war scenario was flying into an environment where it would be visible on radar before it could engage, giving ground-based missile systems time to respond before the aircraft completed its mission. The Air Force looked at these two developments together and concluded that the next-generation fighter needed to address both simultaneously. It needed to be able to defeat advanced Soviet fighters in close combat, and it needed to be able to penetrate defended airspace without being destroyed by the surface-to-air missile systems guarding it. The answer to both requirements pointed in the same direction. If the aircraft could not be detected by radar, the surface-to-air missile systems could not engage it. If the aircraft could not be detected by radar, enemy fighters could not position themselves for an attack until it was too late. Low observability, what the engineers and planners called stealth, was not a feature added to an otherwise conventional design. It was the foundational requirement around which every other aspect of the aircraft would be built. In September of 1985, the Air Force formally issued the request for proposals for what it was calling the Advanced Tactical Fighter, or ATF. The requirements were precise and demanding. Supercruise, meaning the ability to fly at sustained supersonic speeds without using afterburners. A combat radius greater than 600 miles. Stealth sufficient to penetrate advanced Soviet air defenses, and close combat maneuverability that could defeat the MiG-29 and Su-27. No aircraft in existence could do all four of those things. Building one that could would require solving problems in materials science, engine design, aerodynamics, and avionics architecture that had never been solved before. In some cases, problems that had never been seriously attempted. 7 companies submitted initial responses. The Air Force narrowed the field to 2 teams. On one side was Lockheed, working through its Skunk Works division at Burbank, California, partnered with Boeing and General Dynamics. On the other side was Northrop, partnered with McDonnell Douglas. Each team was given funding to build and fly 2 demonstrator aircraft. The Lockheed team produced the YF-22. The Northrop team produced the YF-23. Both aircraft made their first flights in the autumn of 1990. Both met or exceeded every performance threshold in the ATF requirements. The evaluators found that the YF-23 was slightly stealthier and slightly faster. They found that the YF-22, with its 2-dimensional thrust vectoring nozzles, was more maneuverable, had flown more test sorties, and was judged to carry less development risk. On April 23, 1991, the Secretary of the Air Force announced that the Lockheed team had won the ATF competition. The aircraft would be designated the F-22. Its development phase would take 6 more years, cost billions more dollars, and encounter problems that no one had anticipated. What emerged from that process would redefine what an air superiority fighter could be. To understand why the F-22 is what it is, you need to understand how radar works and why it has been the decisive technology in air combat since the 1940s. Radar works by transmitting radio waves outward, waiting for those waves to bounce off an object and measuring the time it takes for the reflected signal to return. The strength of the return signal, combined with the time of travel, tells the radar operator where the target is, how fast it is moving, and roughly how large it is. The measure of how detectable an object is by radar is called its radar cross-section, and it is measured in square meters. A large radar cross-section means a strong return signal and easy detection at long range. A small radar cross-section means a weak return signal and detection only at close range, if at all. A conventional fighter aircraft like the F-15 has a radar cross-section in the range of 10 to 20 square meters. An F-15 is a large metal aircraft with flat surfaces, right-angled joints between wing and fuselage, exposed engine inlets that give radar waves a direct view of the rotating fan faces of the turbine, and external weapons hanging from pylons that each create their own radar return. Modern radar systems can detect an F-15 at ranges exceeding 200 miles under the right conditions. The F-22 has an estimated radar cross-section of approximately 0.0001 square meters. This is roughly the equivalent of a bumblebee. At that cross-section, a ground-based radar, or an enemy fighter's radar, would need to be at extremely close range under optimal conditions to generate a reliable return, and the conditions in combat are rarely optimal. For practical purposes, the F-22 is invisible to the radar systems it was designed to defeat. Getting from an F-15's radar cross-section to the F-22's required solving two separate and equally difficult problems: shaping and coding. Shaping comes first and accounts for the larger portion of the reduction. A conventional aircraft has many surfaces that are nearly perpendicular to the line of sight from a radar transmitter, and perpendicular surfaces reflect radar energy directly back toward the source, producing a strong return. The F-22's airframe was designed from the beginning to eliminate those perpendicular reflections. Every major surface is angled so that incoming radar energy is reflected away from the transmitter rather than back toward it. The leading edges of the wings are swept at precisely calculated angles. The tail fins are canted inward. The lower fuselage is shaped so that there are no flat-bottom panels that would create a strong downward reflection visible to ground-based radar. The engine inlets are particularly important and particularly difficult to manage. Jet engines require large amounts of air, and the inlet ducts leading to the engine face must be wide enough to supply that air. But an inlet duct is essentially a tunnel, and a radar wave entering a conventional inlet duct travels straight to the engine's fan face, where the curved metal blades create an exceptionally strong radar return. The F-22's inlet ducts are shaped in an S-curve, so that the fan faces are never directly visible from outside the aircraft at any angle. The radar wave enters the inlet, hits a curved wall, and is dispersed rather than reflected back. All panel joints and access doors on the aircraft are cut in a sawtooth pattern, so that any radar reflection from a seam or gap is directed at a specific angle that does not return to the transmitter. The cockpit canopy is coated with a thin layer of metallic film that prevents radar from penetrating to the interior and reflecting off the pilot's helmet and the aircraft's avionics. The weapons are carried inside internal bays that are kept sealed during flight, so that there are no external pylons or hanging munitions to create their own radar returns. But shaping alone cannot get a fighter aircraft to the F-22's radar cross-section. The aircraft must also fly through frequencies that shaping is not optimized for, and there are always some surfaces and angles where geometric solutions are insufficient. This is where the radar-absorbent material coating becomes essential. The RAM coating on the F-22 is applied to the specific locations on the airframe where shape alone cannot adequately manage the radar return. The primary locations are the edges of the wings, the leading edges of the control surfaces, the engine exhaust nozzles, and the seam lines where panels meet. The coating works through a fundamentally different mechanism than shaping. Where shaping deflects radar energy away from the transmitter, RAM absorbs it. The material itself is a composite substance containing ferromagnetic particles suspended in a polymer or epoxy matrix. The chemistry is classified and has been continuously refined since the first generation of stealth coatings applied to the F-117 Nighthawk in the 1970s. When a radar wave strikes the surface of the coating, it penetrates into the material rather than reflecting off the surface. Inside the coating, the ferromagnetic particles interact with the electromagnetic energy of the radar wave and convert it into heat through a process of magnetic hysteresis, the repeated oscillation of the magnetic domains within the material as the wave's energy passes through them. The heat is then dissipated into the airframe. The radar wave has been absorbed. There is nothing left to reflect back to the transmitter. The ceramic matrix RAM on the F-22's engine exhaust nozzles is specifically formulated for high-temperature environments because the nozzle area reaches extreme temperatures during operation, and a coating that degrades under heat would rapidly lose its absorptive properties. This is one of the reasons the F-22's exhaust nozzles have a distinctive two-dimensional flat shape rather than the circular nozzles of conventional jet engines. The two-dimensional shape both reduces the infrared signature of the exhaust and allows the RAM coating to be applied more effectively to a geometrically simpler surface. The F-22's radome, the nose cone that protects the radar antenna, is engineered with a low bandpass design that transmits only the specific radar frequencies the F-22's own APG-77 system uses. Incoming radar waves at any other frequency strike the radome and are absorbed rather than transmitted through to the antenna. This means that even the nose of the aircraft, which contains a large, complex radar system, does not create a significant radar return when illuminated from outside. The practical result of these systems working together is that the F-22 approaches a target at supersonic speed, sees the target on its own radar at ranges that may exceed 300 miles, fires missiles from a distance at which the target's pilot has no indication that a threat aircraft is present, and exits the engagement zone before the target's wingman can determine where the shot came from. This is what the Air Force means by first look, first shot, first kill. It is not a slogan. It is an operational description of how the F-22 fights, and it is only possible because of the combination of shaping and coating that makes the aircraft effectively invisible to the radar systems of its opponents. Stealth makes the F-22 invisible. The Pratt & Whitney F-119 engine makes it unstoppable once it gets there. The conventional way to fly a fighter aircraft at supersonic speed is to engage the afterburner. An afterburner is essentially a second combustion stage attached to the rear of the engine, where additional fuel is sprayed directly into the hot exhaust stream and ignited. The resulting combustion generates enormous additional thrust and allows the aircraft to accelerate through and sustain supersonic speeds. The problem with afterburner is that it burns fuel at a rate several times higher than the engine burns at normal thrust. It generates a visible infrared signature from the flame, and it creates a bright visual signature in the exhaust that is visible for miles. Flying on afterburner is loud, hot, visible, and expensive in fuel. For a stealth aircraft trying to approach a target without being detected, running the afterburner is counterproductive. The F-22 was designed to sustain supersonic cruise, meaning cruise speeds above the speed of sound, without using its afterburner. This capability is called supercruise, and it is one of the most technically demanding requirements of the ATF program. Achieving supercruise requires an engine that produces enough thrust at military power, meaning normal non-afterburner operation, to overcome the drag of supersonic flight without needing supplemental combustion. The F-119 engine that Pratt & Whitney developed to meet this requirement is in the 35,000-pound thrust class per engine at military power. The F-22 carries two of them, producing a combined thrust that gives the aircraft a thrust-to-weight ratio at typical combat weight approaching unity and exceeding unity in full afterburner. This means the aircraft can accelerate vertically when it needs to. It also means that at altitude, in the thin air where the drag of supersonic flight is reduced, the F-119 can sustain speeds above Mach 1.5 without afterburner. The practical combat significance of supercruise is several-fold. A supersonic aircraft is harder to intercept because it reaches its engagement zone faster and exits faster. A supersonic aircraft closing on a target gives that target less time to react. An aircraft cruising at supersonic speed without afterburner is significantly stealthier than one using afterburner because it produces less infrared signature in its exhaust and no afterburner flame. The combination of stealth and speed means the F-22 arrives at the engagement point quickly, is already inside missile range before the target detects it, fires, and departs at supersonic speed before the target's wingmen have confirmed what happened. The F-119 is also the engine that enables the F-22's most visible display of agility, the two-dimensional thrust vectoring nozzle. The nozzle at the rear of each F-119 engine can rotate up to 20 degrees in the pitch axis, redirecting the thrust of the engine upward or downward. At normal flight attitudes and speeds, the flight control surfaces on the wings and tail do the work of maneuvering the aircraft. But at very high angles of attack, the angles at which the nose is pointed far above the direction of flight, the conventional control surfaces lose their effectiveness because the airflow over them is disrupted. The thrust vectoring nozzle continues to function regardless of angle of attack because it is redirecting the engine's thrust, not relying on airflow. This gives the F-22 the ability to point its nose at targets that a conventional aircraft could not track without changing its entire flight path. In a close-range dogfight, the ability to swing the nose to angles that standard aircraft cannot achieve while simultaneously directing that nose toward a target provides an engagement geometry that opponents using conventional control systems simply cannot match. The airframe that houses these engines is composed of approximately 39% titanium by weight and 24% composite materials. Titanium provides the strength-to-weight ratio needed in the highest stress areas of the airframe, including structural bulkheads and the hot sections near the engines. The composite panels are used for the fuselage frame, wing spars, and the honeycomb sandwich skin panels that cover most of the external surface. Composites are lighter than aluminum, stronger than steel per unit weight, and, critically for stealth, they do not reflect radar in the same way that metallic surfaces do. An airframe built primarily of composites can be shaped for low radar cross-section in ways that a metal airframe cannot. Stealth keeps the enemy from seeing the F-22. The avionics system tells the F-22 pilot everything about every threat in the airspace around him, assembled automatically, without requiring the pilot to manage multiple separate sensor systems simultaneously. This is the capability the Air Force calls sensor fusion, and in the F-22, It operates at a level that had no precedent when the aircraft entered service in December of 2005. A conventional fighter pilot in an F-15 or an F-16 manages multiple separate information streams during combat. The radar display shows what the aircraft's own radar is detecting. The radar warning receiver shows what radar frequencies are illuminating the aircraft from outside. The missile launch detector reports incoming missile shots. The communication system provides information from other aircraft and from ground control. In a fast-moving engagement, the pilot must integrate all of this information himself, in real time, under the pressure and cognitive load of high-speed flight and imminent lethal threat. The speed at which a pilot can build and maintain an accurate mental picture of a complex three-dimensional battle space is one of the fundamental limits on fighter effectiveness. Pilots who build that picture faster, who know where every threat is and what it is doing before their opponents do, win. The F-22's avionics architecture was designed to eliminate that limit. Every sensor on the aircraft feeds into a common processing architecture that automatically fuses the information from all sources into a single integrated tactical picture. The APG-77 active electronically scanned array radar contributes its tracking data. The ALR-94 electronic warfare system contributes its passive detection of enemy radar emissions. The AAR-56 infrared and ultraviolet missile launch detector contributes its threat warning data. The communication system contributes off-board information from other F-22s, from airborne warning and control aircraft, and from ground-based intelligence. The fusion processor combines all of these inputs, resolves conflicts between them, identifies targets, assigns threat classifications, and presents the pilot with a single coherent picture on the cockpit displays, showing every tracked contact with its identity, position, velocity, and threat status. The APG-77 is itself a weapon system that goes well beyond detection. It is an active electronically scanned array, meaning that instead of a single radar beam swept mechanically across the sky, it uses an array of 1,956 individual transmit and receive modules, each the size of a stick of chewing gum, that can be steered electronically in nanoseconds to point in any direction within the radar's field of view. The beam can be formed and reformed faster than any mechanical antenna could physically move, allowing the radar to track dozens of separate targets simultaneously while also scanning for new threats. The APG-77 changes its transmit frequency over 1,000 times per second. This makes it an exceptionally difficult radar to detect, because the conventional approach to detecting a radar signal is to measure its frequency and use that measurement to identify the source. When the source changes frequency 1,000 times per second, the detection system cannot lock onto a consistent signal to track. This property is called low probability of intercept. The F-22 can actively illuminate targets with its radar, and those targets' radar warning receivers may not register a coherent warning because the signal they are receiving looks like noise rather than a coherent radar transmission. The APG-77 can also be focused to deliberately overload enemy radar systems. The concentrated energy of the phased array, directed at a specific target, can produce a jamming effect on that target's radar and sensors. The F-22's primary weapon is its missiles, but its radar is also an offensive tool. When the F-22 is ready to engage, the weapons are loaded internally. The main bay under the fuselage carries 6 AIM-120 advanced medium-range air-to-air missiles. Each side of the aircraft contains a smaller bay holding one AIM-9 Sidewinder short-range missile. The missiles are launched through a system that ejects them pneumatically from the bay before the rocket motor ignites, ensuring that the hot gas of ignition does not damage the aircraft's internal structure. The weapons bays open for the minimum time necessary for launch and then close, preserving the aircraft's low radar cross-section throughout and after the engagement. From the target's perspective, the sequence of an engagement with an F-22 proceeds roughly as follows. The F-22 detects the target at long range with its APG-77, while flying in a direction and at an altitude that the target's radar is not scanning. The F-22 builds a firing solution while closing at supersonic speed. At the appropriate range, the weapons bay opens for approximately 1 second. The missile is ejected and ignites, and the bay closes. The target receives its first indication of danger when the AIM-120's own active radar seeker, which activates in the terminal phase of flight, illuminates it from a direction and at a range that leaves no time for effective evasive action. In many exercise scenarios, the target's pilot never receives a warning indication at all before the simulated missile arrives. This is what the Air Force means when it says the F-22 provides air dominance rather than air superiority. Superiority means you can win the fight. Dominance means the opponent cannot meaningfully contest the airspace you occupy. In every exercise conducted since the F-22 entered service, it has dominated. On September 7, 1997, F-22 Chief Test Pilot Paul Metz climbed into the cockpit at Lockheed Martin's facility in Marietta, Georgia, and flew the first full-scale engineering and manufacturing development aircraft for 58 minutes. When he taxied back in, he tapped the brakes at a turn in the taxiway, and the nose of the aircraft dipped briefly toward the crowd. Some of the people watching described it as a bow. The aircraft that had taken 16 years from initial specification to first flight was now real and airborne. It would take 8 more years of testing before it entered service, and it would never, under any circumstances, be available to anyone but the United States Air Force. In 1998, the year after that first flight, Congress passed the National Defense Appropriations Act for fiscal year 1999. Buried in its text was a provision known as the Obey Amendment, named for the Wisconsin congressman who sponsored it. The Obey Amendment prohibited the use of any funds made available in that act, or in any subsequent Defense Appropriations Act, to approve or license the sale of the F-22 to any foreign government. It was not a temporary measure. It was written as a permanent ban, and it has been renewed in every defense appropriations bill since. The logic behind the ban was straightforward and has been articulated consistently by military officials and members of Congress across 4 administrations. The F-22 represented a generational advantage in air combat capability, one that the United States had spent decades and tens of billions of dollars to develop. The specific combination of the RAM coding chemistry, the sensor fusion architecture, the avionics integration, and the engine design contained classified information at the highest levels of compartmentalization. Once an aircraft is exported, the United States has diminished control over where it goes, who services it, what happens if it is forced down in hostile territory, and who might eventually gain access to its technology through espionage, accident, or the complex subcontracting chains that defense procurement involves. The example of the F-117 Nighthawk was already on the table by the time the Obey Amendment passed. In March of 1999, a Serbian surface-to-air missile battery using a Soviet-era radar system that operated at frequencies the F-117 Stealth was less effective against shot down an F-117 over Yugoslavia. The wreckage scattered across Serbian farmland. Chinese intelligence personnel visited the crash site. Analysts later assessed that the debris contributed to China's understanding of American stealth technology and influenced the development of the J-20, China's own fifth-generation fighter program, which began producing aircraft more than a decade after that crash. The lesson was not lost on anyone thinking about what would happen if an F-22 went down in non-American territory, or even in the territory of a close ally that might not be able to guarantee the security of every component. Japan wanted the F-22. Japan's request was not casual. Japan Air Self-Defense Force officials and Japanese politicians stated publicly, repeatedly, through the 2000s, that the F-22 was the aircraft Japan needed to counter the air threat from China. Air Chief Marshal Angus Houston, head of the Australian Defence Force, said in 2004 that the F-22 would be the most remarkable fighter aircraft ever built. Australian defence officials and politicians lobbied for access to it through much of that decade. Israel analyzed the aircraft for years and at one point reportedly hoped to acquire as many as 50 of them. South Korea expressed interest. Each of them was told no. The formal reason was always the Obey Amendment. Congress had spoken, and the executive branch did not seek to reverse the ban. But the strategic reasoning ran deeper than the legislation. The F-22's advantage over fourth-generation fighters, including the best fourth-generation fighters flown by adversary nations, was so decisive that its mere existence changed the strategic calculations of every air force in the world that might eventually face American air power. The aircraft that was in service, the aircraft that American pilots were flying, was qualitatively superior to anything any adversary could field. Selling it to allies would require sharing the technology that made it superior. Sharing that technology meant that technology could eventually find its way to the people it was designed to deny. The Allies received the F-35 instead. The F-35 Lightning II was designed from the beginning as an internationally exportable aircraft. It was conceived as a multinational program, with Allied nations contributing to its development costs and receiving work share in its production. Its technology is less sensitive than the F-22's. Its stealth performance is meaningful, but not at the same level. It is a multi-role aircraft that can drop bombs, jam enemy communications, and conduct surveillance missions in addition to air-to-air combat. It is a capable and effective aircraft that is genuinely useful in a wide range of scenarios. It is not the F-22. The distinction matters in specific scenarios, particularly the scenarios most likely to involve Allied air forces in the next decade. Contested airspace over the Taiwan Strait, the South China Sea, or the Korean Peninsula, where adversaries are fielding fifth-generation aircraft of their own, where surface-to-air missile systems are dense and sophisticated, and where the aircraft that can penetrate defended airspace undetected and engage enemy fighters before being detected will determine the outcome. In those scenarios, the F-22's combination of stealth, supercruise, and sensor fusion provides an advantage that the F-35, excellent as it is, does not fully replicate. The consequence of the export ban that its critics have pressed most forcefully is the production number. The Air Force originally planned to buy 750 F-22s. Under the pressure of post-Cold War defense budget cuts, that number was reduced to 381. Under the pressure of Secretary of Defense Robert Gates's insistence that the money would be better spent on the F-35 and other platforms, the final order was capped at 187 production aircraft. The total program, including test and development aircraft, produced 195 F-22s before the production line closed in May of 2012. Exports would not have saved the program from budget pressure, but they would have helped. When Japan was buying F-35s, it was buying several hundred of them. South Korea bought dozens. Australia bought dozens. Those orders kept the F-35 production line running, spread the fixed costs of production across a larger number of aircraft, drove down the per-unit cost, and kept the supply chain and the workforce intact. The F-22 had no such orders to draw on. It was built exclusively for the United States Air Force in numbers that the Air Force itself could not sustain in the face of congressional pressure. By the time production ended, the unit cost of the F-22, including all development costs divided across the production run, was approximately $340 million per aircraft. That is the cost of building 187 aircraft when you spent $66 billion developing it. Had the production run been 381 aircraft, the per-unit cost would have been significantly lower. Had it been 500 aircraft, including exports to Japan and Australia, lower still. The production line closed anyway. The workforce dispersed. The specialized tooling and manufacturing processes developed over decades were either mothballed or lost. A 2010 estimate suggested that restarting F-22 production for a limited export run of approximately 40 aircraft would cost more than $2.5 billion per aircraft at current dollars. That number effectively ended any serious discussion of reopening the line. In 2018, Lockheed Martin proposed a hybrid aircraft to Japan that would combine the F-22's airframe with the avionics and improved stealth coatings of the F-35. Japan was interested. The proposal was evaluated by both the Japan Air Self-Defense Force and the United States Air Force. It went nowhere. The export ban remained in place. The cost of the proposal was prohibitive. Japan ultimately chose to develop its own sixth-generation fighter program, rather than continue waiting for American approval to buy the aircraft its pilots had wanted for 20 years. On February 3, 2023, an F-22 pilot flying off the coast of South Carolina fired an AIM-9X Sidewinder missile at a slow-moving balloon. The balloon had been tracked crossing the continental United States from west to east for several days before the decision was made to shoot it down. The Pentagon identified it as a Chinese surveillance balloon. The F-22 destroyed it at an altitude of approximately 60,000 feet. It was the F-22's first air-to-air kill. For 17 years after entering service, the F-22 had flown in combat. It flew missions over Syria beginning in 2014, striking Islamic State targets and operating in airspace where Russian air defense systems were active. The Russian systems were never able to track it reliably. It had served as the vanguard aircraft in American combat air patrols across the Indo-Pacific, deployed repeatedly to Japan, South Korea, and Guam, as a visible signal of American capability in a region where China was rapidly expanding its own air power. It had accumulated more than 500,000 flight hours. It had participated in exercises that produced the kill ratios that made other air forces study their tactics in detail to understand what had gone wrong. But it had never fired at another aircraft in combat until the balloon. The absence of a combat record against an adversary air force is not a weakness. It is a measure of deterrence. No air force in the world has chosen to contest airspace that F-22s are known to occupy. The aircraft's reputation, built in exercises and confirmed by the Air Force's own assessments and those of allied intelligence agencies, is sufficient to make the calculation straightforward. In any scenario where F-22s are present in force, opposing fighters will be at an overwhelming tactical disadvantage. Adversary air doctrine has adapted not by finding ways to beat the F-22, but by finding ways to avoid direct engagement with it, using long-range surface-to-air missiles, electronic warfare, and numbers rather than aircraft performance. This is the definition of dominance. You have not won when you have defeated the opponent. You have won when the opponent has decided the contest is not worth having. The Air Force has been managing the F-22 fleet carefully since production ended. The aircraft requires extensive maintenance. The RAM coating is sensitive to moisture, abrasion, and the mechanical stresses of high-speed flight in varied weather. Maintaining the coating in effective condition requires specialized facilities, specialized personnel, and significant time. Estimates of the maintenance burden have ranged from 30 to 40 maintenance hours per flight hour, a ratio that is higher than the F-35 and far higher than fourth-generation fighters. An aircraft that spends 30 hours on the ground for every hour in the air requires a much larger maintenance organization to keep a given number of aircraft mission-capable at any given time. The Air Force has invested more than $1 billion in programs to improve the durability of the RAM coating and reduce the maintenance burden. Results have been encouraging, but the fundamental physics of a coating that works by interacting with electromagnetic energy at the molecular level makes it inherently more demanding to maintain than a conventional paint or structural finish. The coating is doing something complicated, and complicated things require more care. 187 production F-22s now carry the entire burden of American air dominance in the high-end threat environment. In the Indo-Pacific, where American and Allied forces might need to contest airspace against Chinese fifth-generation fighters and the dense air defense networks that China has built over the past 2 decades, 187 F-22s, distributed across 7 bases, are the answer to a threat that numbers in the hundreds of aircraft and thousands of missile systems. The Air Force is developing the successor. It is called the Next Generation Air Dominance Platform, and it has been under development since the late 2010s under a classification level that makes the F-22's classified systems look transparent by comparison. The Air Force has said that the F-47, as the production aircraft will apparently be designated, will begin replacing the F-22 in the 2030s. It will incorporate the lessons of the F-22's 20 years of service and the technologies that have emerged in the years since the F-22's design was finalized. It will be faster, stealthier, more capable, and even more expensive. But the F-22 will fly alongside it for years before the transition is complete. The aircraft that Lockheed built in Marietta, Georgia, that first flew on a Sunday morning with its gear down, that taxied back and appeared to bow to the crowd, will continue to be the most capable air superiority fighter that has ever entered operational service. The allies who wanted it and were refused will still be flying F-35s. The adversaries who have tried to find answers to it will still be trying. And the 187 aircraft that America kept entirely for itself will continue to be the reason why, in the places that matter most, the airspace belongs to us. America built a fighter too dangerous to sell to its allies. Whether that was the right decision depends on who you ask and what happens next. What is not in dispute is what Lockheed built, an aircraft that moved the threshold of what air combat can be, that made detection the decisive variable, and then solved detection so completely that its opponents had to change their entire doctrine to avoid it. That is not a weapon system. That is a statement about what American engineering, given time and money and an adversary worthy of the effort, is capable of producing.